Imagine you have a backpack that can hold at most C kilograms. There are n different toys you could put in it. Each toy I has a weight W sub I, how heavy it is, and a value V sub I, how much fun you get from it. The goal of the knapsack problem is to choose a set of toys that fits in the backpack. That is, the total weight sum W sub I less than or equal to C, while making the total value sum V sub I as large as possible. There are two common versions. 0-1 knapsack, you either take a whole toy or leave it completely. No breaking a toy in half. Mathematically, we decide a binary variable x sub I belongs to the set 0, 1 for each item, and maximize sum V sub I x sub I, subject to sum W sub I x sub I less than or equal to C. Fractional knapsack, you are allowed to cut a toy into any fraction you like. Think of a chocolate bar that you can break. Now x sub I can be any real number between 0 and 1, representing the portion taken. The same objective and capacity constraint apply, but the solution can include parts of items. The fractional version is easier because the pieces can be adjusted to fill the remaining space exactly, while the 0-1 version is harder. It is NP complete. The greedy idea is to always pick the item that gives you the most value per unit of weight first. For each item we compute its density. Density I equals VI divided by WI. Think of it like a candy store. You want the candy that gives you the most sweetness for each bite you take. By sorting all items in decreasing order of density, the list tells you which item is the best bang for the buck. The algorithm then looks at this list from the top and keeps taking items until the knapsack is full. This rule is the greedy choice, because at every step it makes the locally best decision without looking ahead. Here is the step-by-step recipe for the fractional knapsack. Compute density D sub I equals V sub I divided by W sub I for every item. Sort the items so that D1 is greater than or equal to D2, greater than or equal to, greater than or equal to Dn. Set remaining capacity R equals C and total value V equals 0. Iterate over the sorted list. If the current item's weight W sub I fits W sub I less than or equal to R, take the whole item. Set X sub I equals 1, update R becomes R minus W sub I and V becomes V plus V sub I. Otherwise, take a fraction of the item. Set X sub I equals R divided by W sub I, the part that fits, add V becomes V plus V sub I times X sub I, and stop because the knapsack is now full, R equals 0. Return the selected fractions x sub I and the maximum value V. The algorithm never looks back. Once an item is taken whole or part, it stays that way. Mathematically, the solution is V star equals the sum for I equals 1 to k minus 1 of V sub I plus V sub k times open bracket C minus the sum for I equals 1 to k minus 1 of W sub I close bracket divided by W sub k, where k is the first item that does not completely fit. This works for any number of items, any capacities, and any values, as allowed to split items. Explanation: to show that the greedy method always gives the best possible value for the fractional knapsack, we use an exchange argument. Assume we have an optimal solution, opt may be different from the greedy solution G, that achieves the maximum total value. List the items in decreasing density order, D1 greater than or equal to D2 ... Dn. Scan both solutions from the top of this list. Find the first index J where opt and G differ, that means colon. In G, we have taken the whole item J or a fraction of it because it still fits. In opt, item J is either not taken at all or only a smaller fraction than G takes. Because G follows the density order, every later item I greater than J has density Di less than or equal to Dj. If opt uses some later item K greater than J to fill the space that G gave to item J, we can exchange part of item K with part of item J, replace a piece of K by the same weight of J. Since Dj greater than or equal to Dk, this exchange does not decrease the total value, it may even increase it. The capacity constraint stays satisfied because we swap equal weights. Repeating this exchange for every mismatch eventually transforms opt into the greedy solution G without lowering the total value. Because we can convert any optimal solution into the greedy one, without losing any value, the greedy solution must itself be optimal. This is a classic proof technique called an exchange argument. In symbols after exchange we have Vj fraction W over Wj plus Vk fraction Wk minus W over Wk greater than or equal to Vj fraction W over Wj plus Vk fraction Wk minus W over Wk, which holds because Vj over Wj greater than or equal to Vk over Wk. Explanation: the greedy rule is not always correct when we are not allowed to split items, the 0-1 knapsack. Here is a tiny counterexample. Item A weight 1 value 6 density 6. Item B weight 2 value 10 density 5. Item C weight 3 value 12 density 4. Assume the knapsack capacity C equals 4. Greedy by density would pick first item A weight 1 value 6 remaining capacity 3. Second item B weight 2 value 10 remaining capacity 1. Item C does not fit, needs 3. Total greedy value equals 16. The optimal 0-1 solution actually picks items B and C. Weights 2 plus 3 equals 5. Too heavy, sorry. We need a feasible set within capacity 4. Let us revise. Better counterexample. Item A weight 2 value 40 density 20. Item B weight 3 value 50 density 16.67. Item C weight 5 value 90 density 18. Capacity C equals 5. Greedy order by density, a 20 C18 B 16.67. Greedy takes a weight 2 value 40 remaining capacity 3. Next C needs weight 5 does not fit, takes B weight 3 value 50. Total equals 90. But the optimal is to take C alone weight 5 value 90, same in this case. Need a stricter, better example. Let us use the classic example. Item 1 weight 10 value 60. Item 2 weight 20 value 100. Item 3 weight 30 value 120. Capacity equals 50. Densities: item 1 6, item 2 5, item 3 4. Greedy picks item 1 weight 10 value 60, then item 2 weight 20 value 100, then item 3 does not fit, needs 30, only 20 left. Total greedy value equals 160. The optimal 0-1 solution picks items 2 and 3. Weights 20 plus 30 equals 50, giving value 220, which is higher than greedy's 160. Thus, for the 0-1 knapsack, simply sorting by value to weight ratio can lead to a suboptimal answer. The reason is that the greedy method may waste capacity on many small density items, while a combination of larger weight items with slightly lower density fits the knapsack better. Even though the greedy rule fails for the general 0/1 case, there are special situations where it does give the optimal answer. All items are divisible. This is exactly the fractional knapsack we proved optimal for. Uniform weight: if every item has the same weight, for example each toy weighs 1 kilogram, then maximizing total value is the same as picking the highest value items first. Sorting by density collapses to sorting by value, which is optimal. Matroid structure: a matroid is a mathematical object that generalizes the idea of independent sets. The classic greedy algorithm theorem says that if the feasible sets of a problem form a matroid and the objective is to maximize the sum of item weights, then the greedy algorithm, pick items in decreasing weight, is optimal. The knapsack with a single capacity does not form a matroid because taking a heavy item can block many lighter ones, but certain restricted versions do, such as the budgeted maximum coverage where each selected item adds a new independent element. Binary knapsack with a canonical weight order: if the weights are powers of 2, 1, 2, 4, 8 and so on, the greedy algorithm works because any capacity can be represented uniquely as a sum of those powers, a binary representation. Taking the largest weight that fits first mirrors the way we write numbers in binary and yields the optimal set. In all these cases, the problem's structure guarantees that no later exchange can improve the solution, so the greedy choice is globally optimal. Sorting the items by their density V sub I over W sub I using any comparison-based sort like quicksort or merge sort costs big O of n log n time, where n is the number of items. Scanning the sorted list once to fill the knapsack. At each step we either take the whole item or a fraction of it, which is a constant time operation. This linear scan costs big O of n. Adding the two phases gives the total time. T of n equals big O of n log n plus big O of n equals big O of n log n. The space usage is minimal. We store the list of items, big O of n memory, and a few extra variables for the remaining capacity and total value. Because the dominant term is the sort, the algorithm is very fast even for large n, far faster than the exponential time dynamic programming needed for the exact 0-1 knapsack. If the items are already given in sorted order, for example a conveyor belt that delivers them by decreasing density, the algorithm runs in linear time, big O of n. Implementation tips. Use a structure or class for an item, weight, value, and a derived field density equals value divided by weight. Store it in an array or list. In languages with a built-in sort, pass a comparator that orders by density descending. While scanning, keep a double remaining equals capacity and double total value equals 0. When you take a fraction, compute fraction equals remaining divided by item.weight, and add total value plus equals item.value times fraction, then break. Watch out for division by 0. An item with 0 weight but positive value would give infinite density. Usually such items are taken automatically. If you need the exact list of fractions taken, store them in a parallel array taken of I, where taken of I is between 0 and 1 inclusive. Common applications. Resource allocation. Suppose a company has a limited budget in several projects, each costing some money called weight and promising a return called value. If the company can invest partially in any project, for example buy a portion of a stock, the greedy fractional knapsack tells it exactly how much to put in each project to maximize profit. Bandwidth sharing. An internet service provider has a fixed amount of bandwidth called capacity. Different users request different amounts of bandwidth and are willing to pay different rates. By allocating bandwidth in decreasing order of payment per megabit, the provider maximizes revenue. Loading a cargo ship with divisible goods, commodities like oil, grain, or liquids can be split. The captain fills the ship by loading the most valuable commodity per ton first. Budgeting for a household. A family has a monthly spending limit. Items like groceries, entertainment, and savings each have a happiness per dollar rating. By spending on the highest happiness per dollar items first, they get the most satisfaction from their money. Knapsack-style games. Many video games let you carry a limited weight of loot, but some items like potions can be stacked partially. The game engine often uses the greedy rule to suggest the best loot combination. Remember, the greedy fractional knapsack works perfectly when you can break items. If you cannot, you need more sophisticated methods such as dynamic programming, branch and bound, or approximation algorithms.